Hello guys, this is Abhijit and today we will continue our discussion on quantum mechanics. In the last lecture I discussed everything about the history of quantum mechanics. Okay, and in this lecture, which I consider is the most important lecture in this series of lecture series, is understanding what is wave function. Okay, many people don't get it. Truthfully speaking, many people don't get it, and also the name wave function is misleading to some extent. So people always try to compare this wave function in quantum mechanics with the wave function that they have studied in their high school, with the like wave equation of a wave on a rope or something like that. But let me tell you this, that this wave function in quantum mechanics is different. It is really different. So we'll understand as we continue forward. So prerequisite has been mentioned here in this screen. You can see and go to my channel and follow these lectures, okay, before you continue with this lecture. So from the last lecture we understood that we have two phenomenon at hand here. Okay, so one is, you learned about particle nature of wave. So what do you mean by particle nature of wave? It says that every wave has some kind of particle linked with it. Every electromagnetic wave, for example, the particle linked with the electromagnetic wave is photons. Agreed. We saw that in the experiment. For example, take photoelectric effect. That was a big experiment that conveyed the message that electromagnetic waves are collection of small energy packets, and these energy packets are photons, and in the experiment they can actually collide with an electron, and we can get photoelectrons. Second is wave nature of particle. Okay, so a particle can show wave nature. We discussed in last class. How do we get it? Remember the interference experiment by electrons? What happened there? Electrons, when the electron beam, when they passed through the slits, they showed the interference pattern. Remember the interference pattern? That was the basic experiment that said that electrons, which are the particles, they are behaving as wave. And I discussed everything in detail in my last lecture, short history of quantum mechanics, of what are the puzzles that are related to the fact that particles can behave as wave. Okay, so let us continue forward. So two phenomena at hand: particle nature of wave, wave nature of particle. And wave nature of particle has something, this equation, concentrate here. This says that if you have a particle, okay, that has a momentum p, okay, the p that you see here is the momentum of the particle, then the corresponding wave nature, okay, will have a wavelength lambda, and the relation between the lambda and the momentum of the particle is given by lambda is equals to h by p. Okay, this is the de Broglie hypothesis. Now continuing forward, so when you understand that particle also behave as wave, you have two ways to visualize it. Now please try to understand this. One way is, either you see the particle as just a particle, a round spherical particle moving at a momentum p, and it goes forward, and the moment you try to think of its wave nature, just forget the particle there, and instead of the particle, imagine a wave moving forward. So either you see the particle as a round classical particle, or if you want to see the wave nature of the particle, forget the particle is there, instead imagine a particular wave of wavelength lambda in place of the particle. Just imagine a wave of wavelength lambda in place of the particle. This is how you imagine. Now you would ask that if the particle is behave as wave, then what is the problem that we cannot imagine particle both as a wave and a particle? it is the problem with our imagination. Like, we cannot imagine 4 dimension because we are so acquainted with our 3-dimensional world. So it's difficult for us to conceive or imagine 4 dimension. Similarly, these are the weird things in nature, that particles behave and wave, and it is our limitation of imagination that we cannot conceive both the thing at the same time. We cannot imagine both the particle and a wave simultaneously. And to manage things with our imagination, what scientists said or what physicists said is, either you imagine a particle as a classical particle, or you imagine the particle as a wave. When you imagine the particle as a wave, forget there is any particle, just there is a wave. Okay, now so now the question is, it's a very simple question anybody would ask. If the electron is a wave, okay, if the electron is a wave, and you also say that the wave has a particular wavelength lambda, then can we write a wave equation for the electron? Okay, like we have a classical equation for the electron has a momentum p. I can write the electron has a velocity v. I can say that v is equals to u plus at for the electron. I can write all the classical equation for the electron, but the moment I imagine the electron as a wave, then why can't I think of writing a wave equation for the electron? It's a logical question. Yes, very difficult. And so let me make you happy. How do I make you happy? I make you happy by saying that, okay, you want to imagine a wave function for a moving electron with a momentum p. Okay, let us take the wave function as psi is equals to a sine kx minus omega t. Okay, now you would say that, hey, wait, you are fooling me. How? Because this is a wave function that I read in my +2, and how the hell is this related with the momentum of the electron or energy of the electron? Yes, it is related. You look at this equation below. Okay, yes, it is related. The k, okay, the k that you see, the k is actually p by h cross. Okay, so the k is indirectly the momentum, and the omega that you see, the omega is indirectly the energy. Okay, the omega that you see, the omega is indirectly the energy of the electron. Agreed? Now, so I think you are happy with the equation. You must be happy with the equation psi is equals to a sine kx minus omega t. So if you are confused with k and omega, then I can also write another equation. Okay, I hope this also makes you happy. I have written everything in terms of energy and momentum of the electron. So I now tell you that this wave function that is inside the green color box that I have drawn is the wave function of the moving electron. Okay, so everybody goes happy. But then one intelligent student asks that, how do you know? How do you know that the electron, that the free electron moving with a momentum p is a monochromatic wave? How do you know that the wave equation is going to look like sine? It can be anything. It can be a cos. Okay, that could have been a phase difference, or you could have said that it could be some e to the power I kx minus omega t. We could written in a complex form. So why is it monochromatic? Yes, a good question. Good question. So I fooled you to make you happy, and then some intelligent student got it. So I'm in trouble now. Well, I need to continue further to make you understand what a wave function is. So P is the momentum of electron and E is the energy of electron. Okay, just for a moment, the poor teacher says the student, just for a moment, trust me and assume that the wave function that is inside the green box is correct. Okay, the teacher says the student, just wait for a moment and assume this equation is correct. The student says, okay, let us assume that this equation is correct and let us move forward. So the now teacher says that, okay, so we had a particle moving at a momentum p, and then what we did is we knew from the quantum mechanics that this particle has a wave nature related to it, and then we guessed a wave function that will define the wave nature of the electron. Okay, now Now we need to go one step further. We want to find a differential equation that is true for the wave of the electron. For example, you know, classical particle, they move with a velocity v or a momentum p, and we have the basic Newton's equation from which all of the classical mechanics can be derived. That is, force is equals to mass into acceleration. This one equation is such that everything, all of the classical mechanics can be derived from this equation. So now the idea is, can we have an equation from where we can derive this psi is equals to a sine kx minus omega t? I mean to say that, can we have a basic equation which relates to the quantum behavior of the electron? For example, the classical behavior of the electron is related to force is equals to mass into acceleration. You know that force is equals to mass into acceleration is a differential equation. Why? Because I can write force is equals to mass and the d square x by dt square. So you see that force into mass into acceleration is a second order differential equation, and by solving the second order differential equation I can derive nearly everything of classical mechanics. So my point of view, my point here is, can I have a basic equation from which I can derive the wave nature of the particle? Okay, so now we set on and we go and look forward towards a basic equation. So what do? We continue further. So how to formulate a fundamental equation for the quantum or the wave behavior, wave type behavior of the classical electron? So what do we do now? So we have this following relation. Keep in mind that since we know that energy is p square by 2m from the classical relation, and from the quantum relation we know that p is equals to h cross k. Okay, so energy becomes h cross square k square divided by 2m. I mean this relation. Okay, and what is energy in terms of omega? Already we have seen. Yeah, remember, let me show you again. Here, okay, here. So can you see this part? Okay, here the energy is related to omega and momentum is related to k. So it's easy. The equation in the red box is very easy. Now, since we know that, since we have assumed our psi, okay, so we forcefully assumed our psi as a sine kx minus omega t. Now by using this assumption, by using this as the solution of the wave nature of the electron, I guess a particular differential machine that can take out the momentum information. Now, can you tell me, in this particular equation, where is the information of momentum? Of course, the information of momentum is with k. The information of momentum is with k. Now how to bring back the k from psi? Well, the trick is, we can use a operator, a second order differential operator that looks like this. Now if I apply it to psi, I get k square psi. Now what is the meaning of this equation? Now this equation says that if the psi has the information of k, then the only way to bring k out of psi is you apply this equation, this derivative, that is a second order derivative, apply it on psi and you get the information of k. You can look it from this equation. Okay, very happy. Point number 1 is done. So we have found a machine or a second order differential operator that can take the value of psi out, value of k out of psi. I mean, it can take the value of momentum out of psi. What now? We need to take out the value of energy. Agreed? Now can you please tell me where the energy is? Well, the energy is with omega. Remember how E was related to omega? So E was h cross omega. So the plan is, what is the operator that can take out omega out? What is the operator that can take omega out of psi? So how about the operator d by dt? It pulls omega, right? It pulls omega. Now question is, why didn't you use d by dx here? Why didn't you use d by dx to pull out k? Big problem. If you use d by dx, no doubt k will come outside, but sine function will change into a cos function. So even if you have pulled out the k outside, the equation is no more a good equation. Things have changed. So the only way is to keep the equation intact and to take out k is to use a second order differential equation. We had no other choice. But pulling out energy was very easy. Pulling out energy was very easy. Just use first order d by dt, use it on psi, nothing happens. Trust me, nothing happens, and omega is easily pulled out. Agreed? So when you apply d by dt on psi, what happens is the omega is pulled out in a very careful manner. Now, so you say that the omega is pulled out by using psi. Okay, but the problem is d by dt upon acting on psi changes the sine function into a cos function. That's another problem. Let us look at this equation. Okay, let us assume this equation for a moment. As we know that d square by dx square pulls out the k and d by dt has the power to pull out the omega, I say that the basic fundamental equation that governs the wave nature is this equation. So what do you actually get from this equation? You actually retrieve this formula from the wave equation. You actually retrieve this formula from the wave equation. Okay, it's very easy. You can easily retrieve this formula. Now, if I say that this relation is the most fundamental relation, okay, then is it possible for me to derive this relation from the following relation? Is it possible for me to derive that relation from this? Let us see if we can do. So what we did is we assumed this as the solution of wave nature of electron, and let us put it in this equation that we assumed that the equation is the basic equation for the wave nature of electron. Okay, so let us see the truth of this equation. So what I have done in this particular derivation is I just applied the value of psi on both sides to check the validity of this equation. I want to check whether the RHS is equals to LHS. Okay, so what I do is, you can see very easily that I have just put the value of psi in both sides, and then I use the operators. I use the differential operator. One, upon using, I get my omega outside, the other brings my k square outside, and then I get an equation which is not consistent, because one side I have the sine and the other side I have the omega, I have the cos. Now you would ask that, hey, look, you made a mistake. Why didn't you took the second order differential equation with respect to time? It could have brought omega square. Okay, and the cos problem would have been solved. Okay, wait, even if you solve the cos problem by taking double differentiation with respect to time, you would get a omega square here. So why would you want a omega square here? Because our aim was to derive this equation. So I don't want a omega square on the left hand side, I need a omega on the left hand side. That's why I used d by dt. and I need a k square on the right hand side. That's why I use d square by dx square. It's quite logical. Okay, but the problem is when I want to derive this equation 2 using the differential operators acting on the wave function that I assume to be true, I face a big problem, and the problem is that the LHS is not equal to RHS, even though I am very near to the answer, because here h cross omega is h cross square k square by 2m. Only if somehow I can make this sine and this cos and this sine both side equal, then I can cancel them. The moment I cancel them, I get my beautiful equation number 2 and everything is good, and I'm very happy with my differential equation that I claim as the fundamental equation of quantum mechanics. So the teacher is disheartened. He wanted to derive a fundamental equation. He came very close. He got h cross omega as h cross square k square by 2m, but the problem with the sine and cos. So how to get out of this problem? An intelligent student said, "Sir, we can do something." I said, "What?" "Why did you took sine kx minus omega t as the fundamental equation?" Okay, why did you took this as the fundamental equation? We can take other equations. The teacher said, "What other equation?" The student said, "Sir, if we use a function like e to the power I k x minus omega t, okay, if we use a function like this, then our problem is solved." I said, "How?" You see, if you use a function like this in both sides, you don't get sine converted into cos or cos converted into sine, no problem. Both sides we get e, and both sides the e gets cancelled, and we happily retrieve equation number 2. We happily retrieve equation number 2. So the whole problem is that we took the sine function. If we take a function like this, you put the function to the differential equation. Where you have to put? You have to put this function into this equation. Then you see that we retrieve our equation number 2. Okay, so we are very happy, things have got solved. We are very much happy. Things have got solved. So this becomes our equation now. We are very much happy. We said that this becomes our equation. You see, the moment you take this as the solution, a small change, if you can see this, if you can compare this equation with that equation, the only change is I put an extra I here, okay, to make LHS equals to RHS. If you want to see, what you do is you put this here and you see whether it is satisfying or not. Okay, how did I get the I here? Because I need to make the LHS equals to RHS. That's why I had to put the I by hand. And now I claim what? Now I claim that this equation in the green box is my fundamental differential equation that governs the wave nature of the electron, and the solution of this differential equation is this: psi is equals to a e to the power I kx minus omega t, and this equation represents the wave nature of the electron, where k contains the information of momentum of electron and omega contains the information of energy of electron. But wait, we face another big problem. You know what is the big problem? The wave function for the electron is complex. This is not a real function. Psi a e to the power I kx minus omega t is a complex function. So the complex function doesn't have any physical interpretation. So we arrived at an equation. This equation 3 is a very good equation because upon applying psi as e to the power I kx minus omega t into this, I get my equation number 2. Remember equation number 2? This was my equation number 2. Okay, I wanted to derive this equation. So to derive this equation, I initially used psi in the sine form, but this didn't help. Then what I did is I moved forward and I took psi in the complex form, and small changes in the basic equation that we took before, slight changes, and we happily arrived at a beautiful equation, equation number 3, that actually gives me equation number 2, assuming that the solution looks like this. So the problem is, we retrieved equation 2 from a basic equation that I call as the Schrodinger equation. The equation number 3 is the Schrodinger equation, but the moment I find an equation that really is compatible with equation number 2, I had to take the solution for the wave function of the electron is complex. It means I had to give up the real function that I wanted to define the wave nature of electron. I had to give it up, and the only choice I had is to use a complex function. Okay, the moment I use a complex function to represent the wave nature of electron, I retrieve a beautiful equation number 3, and that beautiful equation number 3 amazingly gives me equation number 2. And remember, equation number 2 is the most basic fundamental equation of quantum mechanics, because this equation number 2 relates classical mechanics with quantum mechanics. On the left hand side we have energy, which is manifested as h cross omega. That E, when I wrote E, that is the classical one, and when I write E in terms of h cross omega, omega contains the information of frequency. You remember, frequencies are the things that only exist for wave. Frequency, then wavelength, these are the things that are related to wave. So the moment I replace the classical E with h cross omega, I get into the quantum behavior of electron. I get into the wave behavior of electron. And the moment I replace the momentum p square by 2m, and I replace p square with h cross square k square. So what information k contain? K is 2 pi by lambda, and these lambda things are related to wavelength. These lambdas are not related to classical particle. So the moment I replace the momentum of the classical particle with h cross k, where k contains the information of wavelength, it means I inserted here the wave nature of electron. That's why equation 2 is the bridge between my classical equation and the quantum or the wave nature of my electron. Okay, so the equation, the basic fundamental equation that is equivalent to equation number 2 is equation number 3. This equation is equivalent to equation number 2, assuming the solution is complex. Assuming the solution is complex. So, big problem, very big problem. How the hell are we going to define, or we try to understand intuitively, a complex function that is representing the wave nature of electron? It's a big problem. We have still not reached where we should have reached. Okay, a lot of problem. So one problem is, what is the physical meaning of this complex function that is defining the electron? Clearly, if you are using a complex function to define the electron, it is completely crystal clear that this wave function is not your typical wave function that you have studied in your high school. This wave function is complex. It cannot be drawn on pen and paper. You cannot draw a wave for an electron. Please mark my words. You cannot draw a wave for the moving electron, because this wave is complex and it cannot be drawn on pen and paper. Agreed? So the puzzle is, what is psi? What is the wave function psi? What is this complex wave function psi? So in next lecture I'm going to reveal you the actual meaning of psi. Okay, and let me tell you one thing. I proved you here in this lecture that psi is not the wave equation that you read in your high school, this psi is complex, and the equation that you read in your high school are real equations. They are real equations that can be drawn on pen and paper, and this complex function, they cannot be drawn on pen and paper. So forget that this wave function has anything to do with the electron's wave function. This has to be something different. And let me give you a hint. This psi is related to the probability of the measurement. Okay, so that's why I said the name wave function is confusing. This psi is actually related to the experimental result. It has nothing to do with the equation of electron, or it has nothing to do with how the electron is going to look when we think of its wave nature. So in this next lecture